Welcome along once again to Enfield Physics Tutor. Today we're going to look at an A-level question on simple harmonic motion, give you some hints how to handle it. In this question we have a simple vibration generator which is obviously connected to a frequency generator, and the vibration generator is vibrating a spring which has a stiffness constant of K and a mass M hanging on it, and we're given figures for the amplitude at its maximum, the kinetic energy at its maximum, and the frequency of vibration, 5 Hz as it is in this case. In this question we have to find the spring constant K and the mass hanging on the end of the spring. And I always like to begin by writing down some things that we know. For example, omega is 2 pi f. We also know this formula for the velocity at any point along the displacement for a simple harmonic oscillator. Such a useful equation, this one, as we'll see. Everybody's favourite formula is next. Kinetic energy, as always, half mv squared. Since we need to find the mass with which I'm going to start, it occurred to me that we've been given the maximum kinetic energy, in which case if we can find the maximum velocity, then we'll have found the mass, or be able to find the mass. So looking back at the formula for the velocity there, we can say that at the maximum velocity is through the midpoint of a simple harmonic oscillation. In other words, x equals 0, and therefore the formula v equals plus or minus the square root of a squared minus x squared simplifies right down to v max equals omega a. Substituting in the values then, we get 2 pi times 5 times the maximum amplitude, which gives us a maximum velocity of 0.942 meters per second to 3 significant figures. Now it's just a question of rearranging the kinetic energy formula and putting in the values. So 2ek over v squared equals m. And again, time to put in the values will lead us to a mass of 0.14 kilograms, 2 significant figures. So now that we've got m, it's time to move on to find k, and we'll start by using one of the given formulas, that the period is equal to 2 pi times the square root of m over k. Now, a wonderful trick here is to remember that if you invert this, you can get the frequency. So frequency is equal to 1 over 2 pi times the root of k over m. Now we can just rearrange that to get k. So therefore, or implies, that 2 pi f equals the square root of k over m. So now we square both sides, we get 2 pi f squared times m will equal k. And again, time to plug in the values. That gives us a value of k equals 138 newtons per meter. Well, we should round that to 2 significant figures really, so 114 newtons per meter. Next up in this question then, we add a second spring which has a different stiffness to the right hand side of the first one. So we have to find what is the maximum frequency for spring 2, given that we know what it is for spring 1. Well, we start off by remembering that K1 for the left-hand spring was equal to 140 newtons per meter. Therefore, K2 will be a third of that value, which is 47 newton meters. So let's recall then that the frequency is 1 over 2 pi times root m over k. We know that m is fixed and also 1 over 2 pi is obviously. Therefore, we can say that the frequency is proportional to root of the spring constant k. Now we can see that the spring constant going from the first spring to the second spring has changed by a factor of 1/3. Therefore, we can say that the frequency is going to be proportional to the root of 1/3, which comes out at around about 0.58 to 2 significant figures. Given that f1 is equal to 5 Hz, this means that f2 will be equal to 5 times 0.58. Notice I wrote 0.5, which comes out as 2.9 hertz. So our second spring therefore has a frequency of 2.9. The graph shows what happens to spring number 1 as you change the frequency of vibration from, I don't know, something like 1 hertz up to something way beyond 5. You can see a clear peak at 5 hertz. And the question is, what happens to spring 2 if spring 2 is inserted into a column of oil? In other words, the mass of spring 2 is vibrating through oil. The question asks you to make 2 predictions for what the graph for spring 2 will now look like. Well, the first of these is to say that the peak will move to 2.9 hertz because that's its natural resonance peak, or its natural peak of vibration. But along with this, of course, the damping has now been increased by the oil that the mass is moving for. This means that the maximum amplitude will be reduced. Well, there it is. Hopefully that was really helpful for you in your simple harmonic motion work. Perhaps you'd like to suggest a topic that you'd like a video on, or a question that you might like me to take a look at. I'll do my best, but I'm not making any promises. Anyway, thanks for watching, and please do tell all your physics colleagues about these videos that we're making. And don't forget to subscribe. Bye.